And before I go into detail about the talk itself, I would like to show you two videos to start with the big question, where is the similarity? And what you see is on the left-hand side, a toy catapult, as you could do it as a child, to throw small projectiles. And on the right-hand side, you see a slow motion video of a human walking through the picture. And I hope that at the end of this talk, you remember at least the answer to this question, because that's basically core of what I'm doing in my PhD. So hi again, I'm Alexandra. I'm working at the Technical University of Munich in Germany, and we already heard what my title is. So let me pick the first two words here at the end of this title, namely human walking. Why do we actually want to have a look at this topic? We know that human gait, for example, this guy here walking through the woods, is highly efficient and very robust. So that's something that comes naturally to us. We don't think about it because we learn it as children, but we will quickly realize how challenging it actually is to replicate this natural leg dynamics when we look into technical systems. For example, in this case, a lower limb prosthesis, but it also applies to other fields like humanoid robots, exoskeletons, gait rehab devices, or orthosis. And I think this talk fits very, very well directly after the keynote presentation here, because we also try to understand more the biological side to actually improve existing technical systems and take more inspiration from biology than just, for example, taking more powerful actuators to mimic what we see, but also try to understand why it is the way it is and to bring that onto technical systems. Now, before we go more into detail about the research in human gait, we need some background, short revision, I will call it, on what a catapult actually is mechanically seen. And I think you all know how it works. We need three basic elements to build a catapult. We need some kind of elastic element, either a linear or a rotational spring that can store energy. And then we need a block or a frame that can take up all the forces that are arising during this process here. In this case, it's just a wooden frame. And then last but not least, a very important part is the catch. So you see it. I hope you see the laser pointer. We need a catch to actually somehow trigger the release of this catapult. Why do we need that? In this case, it's a ratchet mechanism. We need it to facilitate a slow loading, so we can take our time to put energy into the system at a low power input level. And then at the end, once we decide to unload this catapult, we have a rapid energy release of the entire elastically stored energy. So as I said, slow loading with a low power input over a long period of time. And then at the end, a rapid unloading of the entire stored energy to throw, in this case, a projectile. And now I would like to convince you that humans, while they walk, do exactly the same. We actually use a catapult while we walk. The same system as we saw before, we can also see it here. So on the left, you will in a few seconds see the video again that I showed you in the beginning. On the completely right, you see a schematic representation of the human lower limb segment chain, including the main important muscles that we will talk about today. These are our calf muscles, Gastrocnemius and Soleus. They both end in the Achilles tendon, and they basically actuate our ankle joint while walking. And in the middle, you see the ankle curve, the power curve around the ankle joint. And this is mechanically spoken very simple. It's the moment around the ankle joint times the angular velocity. And when I now start the animation, what you see is during stance, we flex our ankle, and this slowly loads the muscle tendon unit of our calf muscle. So we store elastic energy in our Achilles tendon. And at the end of stance, basically exactly now, we rapidly unload the entire energy stored in our calf muscles to bring our leg into swing. So this swing leg is then the projectile that we saw in the previous video. Now I said that we focus on the two calf muscles today because we had a closer look into what biology actually knows about these two muscles. We know that the soleus muscle, it's the orange one, is a monoarticular muscle. That means it only actuates one joint, in this case, the ankle joint. And we know that the gastrocnemius here in blue is a biarticular muscle. This means this muscle spans two joints. It can actuate the knee and the ankle joint. And as this muscle is pretty long, we have long tendons. This means that the entire system is optimized for elastic properties. So similar to the linear spring in the mechanical catapult, I would call it. And we also know from biology that both muscles show mostly isometric behavior in stance. This means that the muscles are not actively contracting, but they just produce enough effort, so to say, to keep the forces that arise during this passive loading of the tendons, but they do not actively produce a force. And this raises now the question, why do we actually have active muscles here? I mean, we just focused on steady state walking. Of course, evolution has probably its reasons why we have muscles here instead of just tendons. But maybe for steady state walking, and this is, for example, important for prosthesis, it would be enough to have just passive elasticity down there without active muscles at all. We also looked into a second question, namely the muscle contributions, but we will focus only on the first due to time constraints today. And we already heard now biology can do a lot of measurements, they can do observations in human beings, but still this measurement capabilities and also the experiments that you can do due to ethical constraints are limited. So what can we as engineers do? We can use simulations and robotic models, exactly what we heard in the previous talks. What I'm mainly doing is so-called neuromuscular simulations, and we also collaborate with the Max Planck Institute in Stuttgart, for those who know it, to build a robotic model to actually validate what we find in simulation. This talk will today just focus on the simulative part. And for those of you who are not familiar with this neuromuscular simulation type, this is basically you combine a simple multi-body simulation. So in my case, it's here on the left hand, just 2D rigid bars that you connect by revolute joints. That's it. So pretty simple mechanics. But the fancy thing is now to actuate the system, you use muscle models. So you explicitly simulate the muscle tendon dynamics for all the main muscle groups. In our case, we use hill muscle models. And on top of that, we use a neural reflex controller. So we have no centralized brain, so to say, but we rely on local reflexes for the muscles. And once you tune all these reflexes in a proper manner, and that's not so easy, you need a lot of optimization approaches. You need to formulate what is actually steady state. And it's not so trivial to put that into formulas to tell that to your optimizer. But once you do that correctly and you put some effort in tuning all these gains, I will call them, similar to a P gain. If you turn the gain up, you get more force. If you turn it down less, you can do that individually for all the most muscles that you have here. And once you do that, you get this cute stickman here. And you can replicate a pretty natural walking dynamics here, but you also have a lot of degrees of freedom here that you tune on. And that's why we also need hardware validation in a robotic model to actually see if it's still working in real world with friction, with damping, with everything that we don't have in the simulation. Now, as I initially said, the question was, do we actually need active muscles at the ankle joint? And once we use this as a reference solution, so we have all the muscles in simulation, it's pretty easy to test this hypothesis because you can just replace the muscle by a spring. It's very easy. You can't do that in reality, but in simulation you can. So what we did, we replaced first the gastrocnemius, then the soleus, and lastly, both muscles by springs in the simulation, and did no further adaptations. The only thing we had to decide on is spring stiffness and resting length. And you can do that by looking into different curves that you know from the muscles already. And once you do that, the result is, I would say, pretty surprising. You see here this, oops, hopefully the animations, no, go back. It's not working, okay. Then I'll have to play it by hand. Once I click on it here, you see that all the guys are still able to walk, and we did no adaptations. We just replaced the muscles and that's all. And I think that's pretty surprising. We, of course, did detailed analysis on metabolic energy consumption, on how the joints move, compare this to a natural walking gait of a human. And we see it's really possible to walk without any active actuation at the ankle joint, purely passive. And I think for prosthesis or for any technical system, this is cool because replacing an elastic element is just a spring. However, replacing a muscle is pretty complex because artificial muscles are still not really working in the way we wanted and the way they work in humans. Of course, you see some slight deviations, and we discussed it in the paper in detail, but nevertheless, it's, I think, a cool result to show that for steady state walking, we probably don't need active ankle actuation. And we could also put that onto the robotic system. So this guy here has purely passively driven ankle joints. You see here, we have the springs. So we have tendons and spring routings, and we still see this impulsive ankle push-off. So this catapult action that I explained to you in the beginning is still here, even in the total absence of active ankle actuation. And I think that's a pretty cool result. I would refer to this paper here. We also presented at IROS this year. So yeah, pretty interesting results. So to conclude, in theory, at least in the simulation and in the robotic model, we could show that steady state walking indeed is possible without any active ankle actuation. And especially for lower limb prosthesis, this is a pretty cool result, I would say. For the second question, see me in the coffee breaks or read the paper to get more details on that. And with that, I would like to conclude with some important take-home messages. First of all, please remember that the human leg is actually a catapult, and that the two videos in the beginning are showing exactly the same mechanical effect. Then, as I said, probably there is no active ankle actuation needed, at least not for steady state walking. Of course, evolution has probably its reason why we still have muscles down there, but maybe not for walking. And last but not least, if we think more on now, let's say technical system, exoskeleton, prosthesis, gait rehab devices, maybe we should have a closer look into mechanical intelligent design, I call it here. Maybe it's not the best way to put more powerful actuators, more fancy control methods down there because we can. Maybe we should take a step back, look into how biology is actually doing it and taking inspiration from that to improve existing systems and not just making more and more complex things just because we can. So scan the QR code to get more infos on the entire project. Also, the contact details are there. And with this, I would like to conclude. Thanks for listening, and I am open for questions.
So first of all, thanks for this nice presentation. I will refer to this in my personal talk later. You said that you simulated this hill muscle model. Mm-hmm. So now there are a lot of varieties existing. So what properties are you really simulating? Only the spring properties, also damping properties, tiredness of the muscle?
We simulate the most simple model that you can think of. So as far as I remember, I'm not an expert on muscle models here, but it includes damping, yes, and it also includes active contraction, co-contraction, stuff like that. But it's not one of the super fancy models. It's, I think, from 2000 or so. So rather one from the older section in this segment.
Okay, thanks.
I didn't quite understand if you have the possibility to dynamically change the properties of your hardware system. So the spring loading, for example, or angle of attack when you're walking, or if it's a really fixed system in itself, which creates a very fixed walking pattern and speed.
For this system, once you optimize this reference gait, it's one fixed stepping pattern. So one fixed forward velocity, one fixed step length. So it's nothing that you can change on the fly.